Here's another example. This is actually one of my favorite examples. Integer square root. It's nat to nat, and given n, I want to find a z such that z squared is less than or equal to n, but z plus 1 squared is strictly greater than n. So the integer square root of 25 is 5, the integer square root of 26 is 5, so on and so forth. The integer square root of 35 is 5, but the integer square root of 36 is 6. We already have a nice linear search function, so I can say, cool, let's just apply it. Let's do linear search n, and my function is lambda z less than n times z plus 1 squared z plus 1, less than n squared of z plus 1. Well, that works. That's no fun. Let's keep trying. Let's play the same game. Let's introduce a helper z, and again, the purpose of helper is to compute the integer square root of n. Okay, again, how do I know that's its purpose? Because when I define integer square root, all it does is call helper of 0. Okay, so I'm going to have an invariant. My invariant will be that, again, I'm going to do a linear search. All right, I'm going to start at 0, and start at 0, and keep going, but I don't want to go too far. You ever hear these commercials? The car dealer who says, "Come to us. We will be the last place that you look for a car." So this is the same story. All right, so I'm going to have an invariant that says I haven't gone past the integer square root. All right, my guy z here is not too big, and so, well, let's see. All right, it says if n is less than the square of z plus 1, well, then, by golly, I found my guy. Otherwise, I haven't found my guy, so I can call helper of z plus 1. And in fact, look, how do I know that this guy satisfies the invariant? How do I know that z plus 1 squared is less than or equal to n? Well, I just checked it over here. Right? I checked for the negation of that over here. Since this was false, I know that z plus 1 squared must be less than or equal to n. This is not greater than n. And of course, I have a halting measure, which is minus nz. I know that this is non-negative because I know that z squared is less than or equal to n. Right? And since we're only dealing with positive numbers here, I know that means that z itself has got to be less than or equal to n. That's always positive, and z keeps increasing, which means this halting measure keeps decreasing. Again, helper finds the answer for the whole function. The invariant guarantees that the halting measure is non-negative. I update the accumulator to maintain the invariant. And at the beginning, I initialize the accumulator to make the invariant true. It's right. Well, so again, here's a picture. Here's a picture, right? Here is the region from 0 to n, and there's my value z, a helper when I call helper of z, and my invariant is that z squared is less than or equal to n, right? So that means all of the numbers in the shaded area have squares that are less than or equal to n. And again, my task is to grow the shaded area. Now, this code is fine, but we can improve it. Observe that we take the square of z plus 1 at every step, every time through this loop, every recursive call. Let's see if we can keep the value of the square of z plus 1 in an accumulator, which I will call u. It's not obvious that you can do this, but it happens to be true. And once somebody tells you that it's true, it's easy to figure out how to do it. So my new value of z, let's call it z prime, is z plus 1. So that means the next value of u, u prime, should be z plus 1, the quantity squared. Excuse me, z prime plus 1, the quantity squared. Right, because u is supposed to be equal to z plus 1. So when z becomes z prime, u should become u prime. Well, let's see. That's z prime plus 1 times z prime plus 1, which is z plus 1 times z plus 1 plus 1. Binomial theorem, that's equal to z plus 1 squared plus twice z plus 1 plus 1. But z plus 1 squared is equal to u. That was the invariant we were going to try to maintain. So that means as z becomes z plus 1, u should turn into u plus 2z plus 3. 7th grade algebra. And of course, I'm going to use using the fact that u is equal to z plus 1 squared. Here's our new version of integer square root. Same story, but now I've got a slightly more elaborate invariant here. This is where my helper takes two arguments, z and u. And my invariant says, take z and u where z squared is less than or equal to n and u is equal to z plus 1 squared. Well, that's cool. So now I can say, instead of saying less than n z plus 1 squared, I can just say less than n u. Right? And instead of saying helper z plus 1, of course I have to give helper is now a 2-argument function. I have to give it the new argument u, but I just computed that the new value of u should be u plus twice z plus 3. And how do I initialize it? Well, z is still going to be initialized as 0. How am I going to initialize u? Well, u is supposed to be equal to z plus 1 squared. If z is equal to 0, then u should be equal to 1, the quantity squared, which is 1. Yeah? That all okay? Right, let's do my same little old animations. The helper finds the answer for the whole function. I substituted u, I wrote down u instead of z plus 1 squared because I know that those two quantities are equal due to the invariant. The invariant is the condition on the arguments for the function to make sense. So for this function to make sense, u had better be equal to z plus 1 squared. I update the accumulator and I maintain the invariant, and I initialize the accumulators so as to make the invariant true. Z is an accumulator. It keeps track of context. It keeps track of what we've looked at so far. And U here is another kind of accumulator. Right? It's the accumulator that we need to keep track of to maintain our invariant. We could compute it. We could compute U painfully every time, which is what we did in the last version. But in fact, we don't have to. Yeah, okay, we can do this one more time. Sure. Okay, let's do V. Let's add an invariant V equals twice Z plus 3. When Z goes up by 1, how much is V supposed to go up by? 2. Linear algebra. Y equals mx plus b. Right? V is equal to twice Z plus 3. When Z goes up by 1, V goes up by 2. There's the algebra. Cool. All right, so here we have one more time. Z squared is less than or equal to n, and u is equal to z plus 1 squared, and v is equal to twice z plus 3. If n is less than uz, otherwise helper of z plus 1 plus uv, and the new value of v is plus v2. And how do we initialize it? Well, v is equal to twice z plus 3, so if z is equal to 0, what should v be equal to? 3. The invariant tells us how to initialize these guys.